Hi, everybody. So like Laura said, I'm not really an SRE, but some of my friends are SREs, and they heard one of my talks that I did at work, and they thought it might be a good idea if I proposed it here. It's about project scheduling, and apparently SREs do project scheduling in between, I guess, what we call toil. And the idea is to reduce the toil and do more projects. So while I originally composed many of the a lot of the content of this talk for software engineers, I think it applies equally well to people doing any kind of projects. And my job at work right now is, it's hard to describe, but one of the things I do is try to figure out why projects fail. The reason is surprisingly frequently something dumb. And so this talk is about one of the specific types of dumb reasons that projects fail. And by dumb, I mean like completely avoidable, and your project should not have failed if you'd known a few simple things. So I considered some alternative titles for this talk. One of them is Unusual Applications of Queuing Theory, because it turns out that project scheduling is just tasks going into a pipeline and then sort of sporadically coming out the other side of the pipeline. So it's a really unreliable queue, but it really is just a queue. So all the stuff I'm going to show you is kind of, because I really like queuing theory, I map everything back to queuing theory. One of the other titles I considered was Obvious Advice in Retrospect That Seems Profound When Accompanied by Fancy Charts. I didn't use that title because all of my talks could have used that title, and I need to be able to have some way of differentiating between them. But there are a lot of fancy charts, and once you see them, I'll be able to explain why, in fact, the advice is obvious, and it only seems profound because of the charts. So there's 3 sections I want to show you. The first one is about project estimation. The second one is about bug tracking, and I put them in that order on purpose because you don't need bug tracking to do project estimation. Many people find that very surprising. And the third part is about bug triage. So once you're bug tracking, you need to be able to handle your bugs. So the first part is project estimation. And this slide, which I got from Psychology Today, which is one of my favorite sources of what's called a primary source for Wikipedia that can basically be used to justify anything you want. So the title of this article, which is like moderately well written, was Why Goal Setting Doesn't Work. So what they mean by goals is I'm going to finish X by time Y. And the problem with that is you basically can't promise both of those things because something always goes wrong. So if you say I'm going to finish X, you don't really know for sure what time Y is. And if you say you're going to finish by time Y, you don't really know what X is. And setting goals tends to create all sorts of weird, perverse incentives that screw everything up and make you less likely to succeed. The article itself isn't that great, but I have a link in the upper right to a book by W. Edwards Deming. And my slides, I guess, will be available somewhere where you can actually follow that link. But all of Deming's work is really great. It talks a lot about how you can't just set arbitrary goals and have that do something, right? A lot of managers think it's a great idea. Like, my employees will work faster if I set a goal of, like, 10% more sales in the next year, right? But that's not real management. Real management is telling them how to achieve 10% more sales in the next year, not that they need to achieve more, because they already knew they need to achieve more. But if you don't help people with the process, you don't get anywhere. So one of the most important points about project scheduling generally, and this is basically why projects never finish early. And statistically, that's very important, right? Because you'd think, like, if I'm bad at estimating, then some of the time I should be early, and some of the time I should be late. But as we all know, that never happens. We're just always late, right? We're never early. And the reason for that is this thing called student syndrome. And student syndrome, if you've never heard of it, the idea is that at school, your professor will give you a project that's due in a week. And of course, you don't actually do it all week long at a sustained rate. What you do is you wait till the night before, and then you try to do it, and then you fail. And you go to the professor the next day saying, Professor, it was way too hard, we need an extension. Right? And then the professor gives you another extension for another week, and then you wait for 6 days, and then the night before, you try it again, and you finally finish, and then you finish for the next day. Right? So the project was late. And the thing about student syndrome is that you will never finish early because you always have this psychological tendency to delay doing the work until the last minute. Right? So they have this quote here that is from a decent book called Critical Chain about project management. When we used milestones and you knew you had 2 weeks to complete a step, the 2 weeks were yours. I, as the project leader, couldn't do much to push you to finish earlier. If I came after 1 week and started to press, or even asked, You would have reacted as if I were the one who's out of line. There's still a week to go. What do you want from me? Right? So this is an example of setting a goal. We had a really clear amount of work that needed to be done. We gave you plenty of time to do that work. It still didn't get done on time. Or maybe it got done on time occasionally, but it definitely didn't get done early because of this human tendency to not bother doing it any earlier, right? So what were you doing the rest of the week? You weren't just like browsing Facebook or something, right? Well, you might have been a little bit of the time, but probably you were working on something that wasn't your project, that you thought might be important, that you didn't want to have to argue with somebody whether it was actually important, right? You were doing work, but it wasn't the work. And this is what causes projects to fall behind. So there's another famous writing on software scheduling, which I don't know how many people have read The Painless Software Schedules by Joel. Hands? Some people? I highly recommend it. He wrote it probably 18 years ago or something. But it remains true today. And actually, if you go to the webpage, it actually has a little disclaimer at the top saying, like, sorry, I've actually updated this with a new article that has better advice. I recommend don't necessarily pay attention to the newer, better advice. I suggest reading the old advice. You might want to read both, but the newer, better advice has a lot of tools and stuff in it, and the old advice is much more down to earth, like, look, this is how it is. And what he meant by not the place to play psychological games is on a schedule, you often get this situation where the manager is trying to put together the schedule. You go to each of the engineers, ask them for estimates. The estimates turn out, of course, to be way longer than you hoped. And the manager says, hey, could you actually do that in, I don't know, half the time? And the engineer's like, well, I just made up those numbers in the first place, right? So of course they're willing to knock down the estimate. Now they feel pressured, and the manager feels like they've done a good job because, great, now my engineer's motivated, right? And then inevitably you go to build a product, and it doesn't actually get done in half the time. It probably gets done in twice the time, right? But the problem is the manager is a professional negotiator, and the engineer is not, right? So the manager always wins this negotiation, but in the end, nobody wins, right? So the whole point of Joel's article is like, look, we need to get the psychological games out of scheduling. My quote, which I made around the same time, but no, I'm not nearly as famous, is the schedule is absolutely the place to play psychological games, but you have to play to win. And what I mean by that is not that Joel's wrong, but that the psychological games, schedule is filled with psychological games. But if you play the right psychological games, you can get accurate estimates instead of inaccurate estimates, right? So we have to learn how to play these psychological games, and that's sort of what I'm going to be talking about here. I want to do some audience participation. How many of you have heard of story points? Excellent. All right. How tall is the third rectangle from the left? Any other answers? 1. All right, so I've heard of 1, I've heard 3. 3 of what? 2 of what? What's the unit? Oranges. All right, I don't see any oranges in the graph, but maybe there are oranges. Right, how many centimeters tall is that rectangle? 7 centimeters. It depends on the size of the screen, right? And so I'm actually looking at 3 different screens right now showing that rectangle, and they all have different sizes. So if we're going to estimate the size of that rectangle in centimeters, we're going to have to talk about the sort of the average screen with 5 years of experience, right? So how long would it take how big would the rectangle be on the average screen with 5 years of experience? Well, it's about, I don't know, maybe 15 centimeters tall or something like that, right? And that's a lot harder. The first answer I heard was 3. Why did you say 3? Does anyone have an answer? Okay. That's one answer. Would you say the next box is 4? Are there any other guesses for the next box? Right. And why are you saying 5? Pardon me? Okay. That's true. The Fibonacci story points. My sort of goal with this example is to show that it's really easy to see the relative sizes of these boxes, right? If you say the first box is 1, which you could or you don't have to, right? But it's really easy to see that the third box is about 3 times as big as the first box, and that the last box is about 5 times-ish as big as the first box, right? Humans are super, super good at relative size estimation. They're much better than you would even think at relative size estimation. But what humans are really bad at is absolute size estimation. And that's why when I bring up centimeters, for example, it's just, first of all, really hard to just eyeball it and say how many centimeters tall that thing is. But also, the number of centimeters depends on the screen that it's on, or in a project, the number of days a task will take depends on who you give it to, how busy they are, blah, 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 right? But you can always say, with surprisingly high accuracy, like if I'm asking you to build a mobile app that does this, 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 and this, and you've built another mobile app before that does, similar sorts of things, you can say this project is about half as big, it's about twice as big, it's about 2/3 as big, right? People are actually way better at that than you think they would be. And that's sort of the secret of software estimation. And this idea, this concept comes to us from Agile. It's documented really well in a blog post by a person who doesn't like to be named in public, so they have an anonymous blog, but you can Google it. It's called Estimating Like an Adult, and it's a really good blog post about this sort of concept. So I want to emphasize, so people are really good at these ratio concepts. If you know one thing, you can say if this is bigger or smaller, right? People are not very good at absolute values. So if you don't want to have them estimating tasks in absolute values like days or hours, because that directly leads to student syndrome. And the idea of sandbagging, which is the more experience you get, the more you add to your estimate because you know something always goes wrong, right? So more experienced people always make projects sound like they'll be bigger and scarier, which is probably true because they are always bigger and scarier than you thought. But because of student syndrome, it just makes the project bigger when you do that, right? So that's why, one of the reasons why companies filled with experienced people end up doing projects more slowly. Because, in fact, they estimated it would take longer, and student syndrome made that happen, because we're all students on some level, right? I recommend against the small, medium, large sort of scaling, because they're not ratios, right? Like, how many smalls fit inside a large? We all have some idea of what the answer to that question is. The problem is we all have a different idea of what that answer is, right? Where it's really easy to say, like, 5 contains 5 ones. And that makes a big difference when you're estimating. So one of the tricks of estimating is to, once you've got these relative sizes, not think about how much time they translate into. Because as an engineer, as soon as you think about how much time they translate into, now you're calculating a deadline. That deadline or goal is going to cause you to do student syndrome and lose, right? So as a developer, you just have to estimate the task and then forget about it. Your project manager will secretly, behind the scenes, figure out how long it takes you to do a point, make an estimate, and then not tell you what the answer is, right? They'll report it to your manager or the executives or something like that, but they won't tell you because you are just going to do your work. And you won't ever feel like you missed a deadline because, if you estimated 3 points and it turned out to be 4 points, how can you tell, right? And that's really important. That prevents the sandbagging, that prevents the student syndrome, and that means that some of the time you're going to be below and some of the time you're going to be above, and if you add enough stories together, they average out. That's the huge difference. This is the only important part of Agile, actually, is what's on this slide, right? Use story points and not absolute estimates. I don't know if I can overestimate that. Most people think I'm crazy when I say that's the most important thing about scheduling, but it really is. Don't use time, use relative numbers. So what is a story? A story is the smallest bit of functionality delivered to a customer. And this is another thing that is surprisingly complicated about stories, right? People don't really realize this. It has to be delivered to a customer, and that sets a lower limit on how big a story can be, right? If it's going to be something you deliver to an actual person to actually do stuff, that's quite a bit of work, especially if you're starting from scratch, right? Like one project I worked on, we were doing a money transfer system, right? So we were making a mobile app that lets you send money from one person to another who's also using that app, right? So the smallest story we could come up with is we're going to make an app that talks to the back end and pretends to send money, but not real money because we haven't linked it to a banking system yet, right? So what's the simplest app we can possibly make that will actually let you send fake money from one person to another? And the target customer in this case is our coworkers, right? But that's actually a lot of work, right? We're bringing up backends, we're writing a mobile app, we're building a build system, there's a test system, there's, setting up version control. All of that is one story, right? That's super important because one story is the smallest unit you can talk about, but that's what you need to be estimating. So how long does it take you to build this kind of basic mobile app versus another mobile app you've built in the past? And people are surprisingly good at estimating relative sizes of projects like that, right? And it doesn't take you very long. You only have to come up with one number for probably a couple months of work, right? That's what makes this method really powerful, right? So the customer must actually be impacted. The idea of a story, I don't actually write down my stories as stories. I kind of find that a little bit juvenile, that aspect of Agile where you have to write, like, Bob did this and he blah, 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 right? I can just say, like, the user can do this. That's my story, right? And a story is not the same as a bug, a task, or a ticket. We need to process those. That's like part 2. But you don't need to break things down into that level of detail to estimate how long a project will take. That is the magical part of this. So here's one of my really fancy-looking graphs. It takes a little bit of staring at it to see what it's doing. But the idea is, if a story is made up of a series of tasks, which it generally is, and a milestone is made up of some relatively small number of stories, then we're showing over time the reduction in the remaining number of tasks in this story. When it hits 0, then we can launch, right? So this is called a burn down chart. It's a series of burn down charts. And what I'm showing here is the burn down chart under a few different conditions. The first one is I picked a few stories, in this case I think it was 3, up front, and then didn't change my mind and just did all the bugs that apply to those stories. Now, as inevitably, like I wrote this simulation, by the way. So I wrote a program to produce this graph based on somewhat realistic conditions. So over time, bugs are getting filed in your product in all of the features. And so that's why the lines are not quite straight. So I'm working on stuff, and I do fix things. I have a team of 10 developers or something like that, and they're fixing bugs. And every now and then, bugs will come in. So it kind of goes up, kind of goes down. But they made up their mind up front, and they finished the project directly. The second one is more realistic in that we started with 3 features, and then on day 30 or so, we changed our mind about one of the features, we dropped it out, and brought in a different feature instead. And that caused the number of bugs we have to finish to suddenly spike upwards. And then we didn't change our mind again, so it continued to go back down. The third one is we did the same thing, but only at day 100 instead. And it's really interesting to see, and we all know this intuitively, right? But it's interesting to see that the spike is much bigger when you changed your mind a lot later. And that's because there's a bunch of tasks that applied only to feature number 3 that was not in the list before that we didn't even start on. So suddenly we've got this huge number of tasks that we've added versus before where when we changed it earlier, we hadn't made that much progress, so things hadn't built up as much when we switched tasks. The fourth one is actually, interestingly, the completion date, incidentally, is the date it hits 0. So you can see in the fourth one, it actually finishes before the third one. And the fourth one is actually a different example where the product managers basically couldn't make up their mind, and they spent the first 50 days just changing their mind constantly while we were trying to work on the project, right? So you can see like all these little sawtooths every time they dropped out a feature and added another feature, right? So basically we couldn't make any progress because they kept changing their mind on what progress meant, right? But then when they finally made up their mind on day 50, they stopped and continued forward. And that's actually better than a single change on day 100, right? And that's super interesting, right? That in itself, it says something. It says it's better to spend a lot of time up front thinking about what you actually want than it is to change your mind at the last minute, right? And then the fifth one is actually much more like my experience at a large company, and I call that complete indecision. So in this case, what happens is you have a product manager and some other people who made a decision. Then on day 50, some new person comes in and says, hey, guys, have you thought about this? And then they change their mind. And then on day 100, another new person comes in and says, hey, guys, have you thought about this? And they change their mind again. And they keep doing this over and over and over again. And the spikes are the funny shape of the graph. Like, for example, we got pretty close to launching around day 250. And that's only because the spike on day 200 happened to be a little bit lucky because actually they went back and brought in one of the features that they had previously canceled, which didn't add very much work because they'd already done a lot of work on that feature, right? But the point is it never launches. So what actually happens in real life is because we never launch, we decide to sort of cut corners. It's like, look, it's day 300, we still haven't launched anything. Let's launch at all costs, right? Cut out testing, something like that. And so you reduce quality and you get things done. The interesting thing about all the previous examples is that we didn't have to reduce quality, right? We could just finish everything because we knew what we wanted to do. So prioritization is really important. People don't put enough work into prioritization. And I have this really great quote that I found on the internet. It turns out it's not actually by John Maynard Keynes, one of the famous economists, but it's attributed to him. When the facts change, I change my mind. What do you do, sir? And so the flip side of that is when the facts don't change your mind, right? That bottom graph, it's very, very unlikely that the truth of the situation changed every 50 days. What happened is you let people change your mind every 50 days, despite the fact that facts were not changing, right? That kind of lack of decisiveness is what kills projects. So from that, I have advice on how to do project planning. I don't know how many of you recognize the meme on the right, but my advice is similar. List the sequence and the relative size of the stories. Let your project manager convert that into time estimates, but don't tell you what the answer is. And then number 2, do that in that order, right? As a manager, your hardest job is, of course, number 2, and I don't have time to explain to you how to do step 2. But it is actually that simple. When projects don't get done on time, it's because people did not do one of those 2 steps, and it's always step 2. And incidentally, tools for managing your project plan, like fancy Microsoft projects and stuff like that, add nothing. Because stories, you can actually get away with very large stories, which means you have not very many of them, which means just stick them in a spreadsheet and put them in a list and then leave them alone. Or if you want to change your mind, because you're doing the stories one at a time, because they're strictly prioritized, you can reprioritize everything after the first story, and it doesn't impact your launch schedule, right? But you have to get people working on stories in the order that they are in the list, and then get it done as soon as you can, and then move on to the next thing, right? So that's project planning. I have another simulation. This one is even more complicated, if that's possible. And this one comes from Kanban, which is one of the sort of outgrowths of Agile. The only good thing about Kanban, but it's a very good thing, is that it encourages you to not multitask so much. Don't actually try to do 2 things at a time when you could do 1 thing at a time. And this is what this graph is showing. The green area is the total value delivered over time. So you could say that the value delivered is the integral of the value of the product over time, right? So if I've launched a product, value is getting delivered in an ongoing way. If I have not yet launched, no value is being delivered, right? So the green area shows the only thing that's different in each of these 4 graphs is how many features we're trying to work on at the same time, right? So in the first case, we're going to launch after feature number 1 is ready, and then launch version 2 when feature number 2 is ready, and so on. So you can see as soon as feature number 1 finishes, as soon as it hits the y-axis, now we've got a green spot, and we're accumulating value for the company that whole time. And then we launch feature number 2, and we're accumulating even more value because now we have 2 features, so we can presumably get twice as many customers, right? And so on until the end when we've got a really big green dot. The second one is almost as good. We launch 2 features at a time, and you can see we finish at the same time because it's the same number of features, right? Instead of 1 spike, instead of 2 spikes, we have 1 spike, but then the value accumulates, but a little more slowly because we weren't able to launch quite as many things at the beginning. If you do what more people do, which is try to launch 5 features at a time, then you don't get any value until all 5 features are done. And the slope of the line, as you can see, is actually a lot slower because you're trying to work on 5 features at once. And just like in the earlier version of the simulation, people are filing new bugs and things are going wrong at a pretty high rate while you're working on this stuff, right? So you're slowed down by all this parallelism. And then the final one, you decide to launch 8 features at a time, and you never finish. Because it's actually, your team just can't handle doing those 8 features. There's so many bugs being introduced all the time that actually the line is going up and to the right instead of down and to the right. Right? So your burn down chart is actually burning up. And that is, again, a lot more like what happens to projects that I'm familiar with at my company. And the total value delivered in that case is 0. So this is real life, and sort of, it's unintuitive in a way, because you can imagine, like, we talk about this in computer science when you're doing task scheduling on a CPU, right? If you have 2 tasks and only 1 CPU, is it better to time slice between the 2 tasks, or is it better to do them sequentially, assuming that the time slicing overhead is 0, which is not quite realistic, but let's assume that, right? And your throughput is exactly the same in both cases. Let's say you've got 2 tasks that each take 5 minutes, right? It'll take you 10 minutes to finish both tasks. So your task completion rate is 1 task every 5 minutes. But your average latency, if you're multitasking, is going to be 10 minutes because it takes you, if you're switching back and forth, you'll finish both tasks at time 10, right? Whereas if you do one and then the other, you'll finish one task at time 5 and another task at time 10, so your average latency is 7.5, right? Doing things sequentially reduces your latency without impacting your throughput, right? Which is quite a surprising outcome if you haven't seen it before. But it happens in real life as well as in CPU scheduling. OK, so the next section is about bugs. Stories are not bugs. And here's why. Stories happen quite slowly, on the order of like weeks per story. Bugs happen much more quickly. I mean, if you're good at debugging or your bugs are small, they can happen on the order of a few hours, right? So stories are infrequent, bugs are numerous. You have lots and lots of bugs generally in any project. You have not that many stories. Stories are controversial in that the executives and product managers at your company always want to have some sort of input on what stories are get done in what order, right? Bugs are really boring. Product managers really don't want to look at your bug database. Sometimes you make them, and you go to these meetings where you're doing bug scrubs, and they're just, why am I here? I don't care about any of these things. When am I going to get my feature, right? So only engineers actually care about bugs, but we care a lot about bugs. And stories, because there's so few of them, you can track them on index cards in the case of Agile, or I suggest if you've got distributed offices, don't use index cards, just use a spreadsheet. But the idea is, don't do anything complicated. Keep it simple. Don't get distracted by the tools. Bugs, on the other hand, you have so many of them, it's totally impossible to try to track them on paper or using a spreadsheet, right? You need a tool. And everybody kind of knows you need a tool, but it's actually, most of the teams that I've talked to have not found a way of sort of balancing the fact that you want new features to be done in one way and bugs to be done in another way. And you inevitably try to like put your bugs in a spreadsheet, or you try to put your features in the bug tracking system, and neither one ever quite works as well as you'd like it to, right? It always feels kind of awkward. Like, what are those features doing in the bug database? How come nobody ever works on them? So statistically, I need to tell you another thing about bugs. This is another really interesting mathematical effect. Most of us have probably heard of the central limit theorem in passing, but we don't remember what it says. What it says basically is that if you've got a large number of small things and you add them together versus a small number of large things, and the standard deviation and average are the same, then when you've got the large number of things, the cumulative distribution, or the combined distribution has a much smaller standard deviation than if you have a small number of things. So that's really, to me anyway, was really, really non-intuitive. Most people can't believe this is true. So I made another simulation, and this is the results. So in this case, the top graph is stories. Say we've got a total of 5 stories. Each one is between 1 and 13 points, so about an order of magnitude of possible size difference. And you can see we're sort of doing one story at a time. So we finish one, and then we burn down. We only have 4 left. We finish another one quickly. We burn down. We have 3 left, and so on. Until we get to 0. Now, the bottom one is the same project, but counting the bugs instead, right? So there's a lot of bugs. Now, the bugs range between 0.1 and 10 days, right? So a 2 orders of magnitude variation in size, which is a huge variation, right? But because there's so many of them, and because we have multiple developers, and the developers are probably not only working on 1 bug at a time, or sorry, each developer can work on 1 bug, so if you've got 10 developers, you can be working on 10 bugs at a time. You can generally finish bugs at a surprisingly consistent rate, and this is because of the central limit theorem. So I would feel really bad if I didn't have story points, if I didn't know how long each story would take, and I was trying to interpolate that graph on the top between x equals 0, y equals 5, and x equals 350 or so, y equals 0. And I tried to guess how many story points we would have finished at any point during the time, and I didn't have actual points, I just had stories. I would not know where we'd be, right? It's really hard to interpolate that line. Whereas the one on the bottom is weirdly straight, right? We've got 2 orders of magnitude variation in size of bugs. But I feel really confident interpolating about how many bugs I will have finished on a given date, despite the fact that we never spent any time estimating how long those bugs would take. It's perfectly fine to just say, like, look, we've been doing this for a month. It looks like we finish bugs at this speed. I think we're going to keep finishing bugs at this speed. Therefore, if we need to finish 100 bugs to finish, it's going to take a linear multiple of the rate. Right? Now, you probably don't believe that this can actually work, because I looked at this, I made this graph, and I'm like, yeah, right. Estimating cannot possibly be this easy. So I went through a bunch of projects at work, and I drew a similar kind of graph. Now, this is called a burn-up graph. It's called that because it's just like a burn-down graph, except it shows the number of bugs that have been filed and the number of bugs that have been fixed. So when you're done, the two numbers will be the same. And so you're kind of like eating up the space consumed. Like the bottom line eats up the space from the top line. So this project is actually the project that I was working on before I started my weird project. It was the embedded software for a hardware platform. And so we ended up at about 1,300 bugs over the course of, looks like 5.5 years or something like that. And so this line, as you can see, the two lines are not perfectly straight. What they are is essentially a series of line segments, right? And I can't tell you much about the history of my project because it's secret, but I can tell you that each change in slope corresponded to a major organizational change. In between major organizational changes, the ingress rate of bugs and the egress rate of bugs was weirdly consistent. We had teams growing, we had teams shrinking, we had people coming out of the team, we had them being replaced, we had vacations, all this stuff. But those line segments kept on being line segments. We're talking about 1,300 bugs, right? And there's just nothing interesting going on. Now, when our project disbanded in about February 2017, you can see that the ingress rate and the egress rate basically went to 0. But it's another line segment, right? You can still predict when we're going to finish, which is never. Here's another project. This one is the burn down rate for just one milestone of somebody's project. So we tagged a bunch of bugs, and we said, we're going to launch when all these bugs are finished. Now, the time when they tagged it was around July 2017, which is toward the right. All the bugs before that show the rate of the time the bug was filed, but not the time it was tagged into the release, right? So these bugs have been accumulating over the course of years. And some of them were fixed over the course of years before we decided that they were actually important for our release. As soon as we finished deciding what's important for our release, this is where prioritization comes in. The whole team that had been fixing basically random stuff for years started working on the stuff that actually matters, right? As soon as they did that, I consider that a major organizational change. The slope of the green line suddenly shot up, right? But it didn't just shoot up. It's a straight line in that much more sharp direction, right? Once we made that change, we could predict within a couple of weeks that it would take a certain number of months to finish the project, right? It's hard to believe this is true, but it's actually true. I predicted, 2 weeks after we made that change that it was going to take 3.5 months or something, and I think I was off by 3 days, right? It's actually very simple math that is strangely reliable, right? Here's another project. This team is a really interesting one, but they have a lot of internal support tickets and stuff like that. So in the course of 6.5 years, they actually had 60,000 tickets, and they were really good at handling those 60,000 tickets. You can see that the red line and the green line are almost always right on top of each other. And so I added a graph on the bottom, which is the usual burn down chart. Even though it's not burning down. But they were accumulating bugs. And you can again see it's a little more jiggly because burn down charts are a little more jiggly than burn up charts. But it's pretty much straight lines. I wouldn't feel too bad interpolating those basically 4 different segments of that line, right? And again, I asked around, and those 4 different segments corresponded to major organizational changes in that team. When they didn't have a major organizational change, the progress was pretty consistent. Okay, so bug scheduling tips. Use stories for long-term schedules. Once you've got a story in progress, you've probably attached a whole bunch of bugs to that story because those are tasks or whatever. You don't have to bother estimating how long those tasks will take. Just count them. Use software that will draw you a burn down chart, and you will almost always be able to predict very accurately when your next story will finish. And people usually want to know when the next release is going to be, much more than they want accurate answers on when the next 5 releases are going to be. And quality needs to be built into every story. You don't have a quality story, if at all possible. What you want to do is make sure that bugs related to quality get piled into the story related to that story, related into the story related to that release. And because once you get on a release, on a predictable release schedule, if you get good at predicting when your releases will be, it becomes a lot easier for you to argue that, don't worry, we have time to fix this bug, because we're actually going to launch at the time that I said. When people don't trust you're going to launch at the time you said, that's when you get all the pressure to start dropping stuff. And we saw that graph earlier when people were working on 8 different things. They couldn't make up their mind, and we were never going to launch, so we just chopped it off one day and said we're going to launch with all the bugs, right? That's actually what happens most of the time, but it happens because you're not doing the scheduling correctly. And regressions and emergencies is a special case. Like, you'll launch something, you thought you had 0 bugs, it didn't actually have 0 bugs, it turned out you broke something in your launch. You still have to fix those first, but everybody already knows that, right? You're not going to be able to nobody's going to be able to talk you out of fixing that regression. And then the last bit is on bug triage. This is a more queuing theory. Bug triage, how many people have heard of bug bankruptcy? Some. So bug bankruptcy is similar to email bankruptcy. Have anybody heard of that one? Okay. The idea is your bug tracking system has so many bugs in it that you just don't think you're ever going to fix them all. You can't handle it anymore. I give up. So you resolve all the bugs as obsolete and say, I'm going to start over. If you still have a problem, please file a new bug, right? And this happens regularly in the open source world. It happens inside companies on new products. And this graph is an example of what happens when you do bug bankruptcy. The burn down graph on the bottom and the burn up graph on the top both show what happens. So we declared bankruptcy in 2015 and basically marked almost all the bugs as done. So you can see the green line suddenly shot up, and that felt really good. And then the number of remaining bugs suddenly shot down by a lot. So we went from like 3,500 down to about 500. So that, like, wow, that's great. We fixed that many in one day. But of course, the fundamental problem wasn't that we had too many bugs. The fundamental problem was that we were fixing bugs a lot slower than we were receiving bugs. And so after the bankruptcy, what happened is the slope remained exactly the same, right? Because there was no major organizational change. We left the organization the same, so the slope of the bug graph stayed the same, right? The ingress rate of the queue is larger than the egress rate of the queue. If you're making a router and you find your queue is full, what you don't do is just throw out everything in the queue to try to make room. Right? It doesn't fix anything because it's going to fill up again right away. Right? Ingress is always greater than egress. So this is the same graph as before, and I'm just pointing out that line is going up and to the right because we're including all of the bugs instead of a fraction of the bugs. The graphs on top only count the bugs that are relevant for our release, and that's what makes it go down and to the right. Everybody's project always has too many bugs. There's no such thing as a project that doesn't have too many bugs unless the project is dead. Right? The line always goes up and to the right. So you have to have a way of dealing with the fact that the line always goes up and to the right. So how we do that is what's called bug triage. I'm sure we've all heard of bug triage. But it's important to realize fixing bugs is really slow. Triaging bugs is really fast. Right? That's the short version of the story. You can't ever fix all the bugs. Fixing bugs requires a lot of expertise. Triaging bugs actually does not require so much expertise. You can find people who are not capable of fixing the bugs that can still triage the bugs by saying, well, it's related to this. This team should probably do it sometime, right? And it's this level of importance and so on. What people get frustrated by is the idea that, well, I'm disorganized now, right? My bug database is just an undifferentiated mess. I'm never going to be able to triage all these thousands and thousands of bugs. I'm just going to get frustrated. That's why they declare bankruptcy, right? Because I'm going to do it better this time. So people, if I leave all my bugs open, and even if I triage them, my bug database is going to get cluttered. Now, true story, I searched Google Images for overrun by bugs, and that was a horrifying experience. I don't recommend it to anyone. This is not the image I found by using that method. I looked for a picture of clutter or something like that. So this is what happens to your bug database, right? So here's some advice I picked up from the more successful teams at work who actually do know how to handle their bug tracking, as opposed to the teams who are declaring bankruptcy all the time. And the most interesting advice I got is as follows. Never look at all the bugs, right? You've got different bug tracking systems call it different things, but you've got a component or a sub-project or an area or something like that. And people will file a bug and it ends up in that area, and now you've got 10,000 bugs in that area. Anybody who thinks you can manage a project by just opening up the bug tracker and saying, show me all the bugs in the renderer from my web browser, right, is never going to get anything done, right? Never look at that. What you use components for is only for the triage, right? So you've got a triage team, and when a bug comes into an area, the triage team looks at the bug and decides what feature or story it's going to get attached to, right? That's the process of triaging. They don't have to decide who's going to work on it. They don't have to decide when it's going to get worked on. They just need to look at the bug and decide which team it goes to. And then if it turns out it was in the wrong component, like this triage team is like, well, look, we're the renderer triage team, but you gave us, like, I don't know, the Linux installer bug, then their job is to just move it to the right component so the other triage team will pick it up. That's what bug components are for. So everybody who's using bug components and like dividing it 50 different ways, so like this bug goes into this component, is actually doing something that is not going to work out for them in the end, because inevitably those components are always going to end up with too many things in them. And there's no overlap between components. So a project is going to be in component A, but actually this bug applies to component A and component B, because you've got 50 different components and they're too granular, and there's no way to specify that they belong to both. Right? So what they recommend you do instead, and most bug trackers nowadays have this feature, is the idea of a tag or a label. Right? So when you're triaging, your job is label the bug with all of the stories that it applies to. Right? And quite frequently, a given bug will apply to multiple stories. Right? And because you're using labels, you can add multiple labels, and you never have to look at it again. Each of these labels can be relatively small. Sooner or later, you're going to do it because it's a story, or you're never going to do it. But either way, you never have to look at these bugs again. People who continually look at the same bugs week after week in a bug triage meeting are missing the point, right? You shouldn't ever have to look at these old bugs over again. And it's perfectly okay to just leave them open. Right? People get really scared about having too many bugs open in their bug tracking system. They want to have all kinds of rules for when we need to resolve the bug. But the truth is, end users who file the bug get really mad if you resolve the bug as won't fix because we don't have time. But they get not mad at all if you set it to priority level 4 or 5 or whatever and never come back. Right? It's another psychology trick. I highly recommend it to anyone. Just lower the priority instead of closing the bug. It means the exact same thing, but your users get less angry. And the bugs don't need to be assigned to someone. This is a perennial argument in software development, but it appears that the successful teams that I've talked to all follow this rule. Don't worry about assigning the bug to someone unless they're actually going to work on it. Right? People with 30 bugs assigned to them aren't actually going to do all those 30 bugs, so you might as well not lie to yourself. Just leave it unassigned, but in a label so that later, when you actually go to work on that stuff, you can assign the bugs in that label. And here's a thing that I discovered. I can't remember which team I was talking to, but you can actually, on some bug tracking systems, and this one is the Google issue tracker that Android uses in the outside world, but I'm sure it works in a bunch of other kinds of things. The idea is to, if you've got a giant backlog of bugs that you have not triaged, or introducing a new triage system, it can be extremely frustrating to try to triage thousands of bugs in one shot. So that's when people tend to declare bankruptcy. It's like, hey, I've got a new idea for how I'm going to triage stuff. Throw away all the old ones. Now it's going to be manageable. I'd recommend not doing that. Instead, come up with what I call a rolling query. Start with just the bugs that were filed more than 2 years ago, for example, and decide to triage those. And then if your query is written correctly and it says more than 2 years ago instead of an absolute date, then tomorrow you're going to have another collection of bugs that you can triage. And the next day you're going to have another collection. And the next day you're going to have another collection. And after 2 years, it's going to go to 0, right? Because you're triaging all the new bugs and the old bugs over time, right? And the slogan you can use, like, it took us 2 years to get into this mess, and it wasn't that much of a problem. It's okay if it takes us 2 years to get out of this mess, right? It's a lot better than a bug bankruptcy where you're actually losing real information. And it becomes completely possible to do this like bite-sized bug triage every day. And it actually feels really good to be triaging old bugs because half the time the old bugs are already fixed. And you know this, right? So now you're marking bugs as fixed instead of obsolete. So your users are happier, and you feel better. And that was the last slide. I do have a super long version, if you can believe it. An even longer version of these slides are available on my website. You can actually just search for Appinware Epic Treatise, which this is, if you want more details on this stuff. Is there any questions in the last minute or so?